A test was performed in April of 2015 at the GATR facility in Huntsville. The purpose of the test was an end-to-end test of the HiDAQ system. It was a joint effort of HiDAQ, PULSAR, Optical Science, Orbital Telemetry, and the GATR teams. Marshall identified a key risk for the high-rate data collection. There was a lack of hardware to collect and record large volumes of fast data. As a result, High Fidelity Data Acquisition Project, or HiDAQ, was created to fill the void. HiDAQ's purpose is to store large data fast, then recover or downlink the data. PULSAR is the downlink. PULSAR is a software-defined radio for the small satellite market. PULSAR is capable of transmitting large data in X or S-band, but only S-band was used for this test. The full 5-stack PULSAR has an S-band receiver as well. The testing was performed at the GATR facility in South Huntsville. Pictured below is the GATR antenna. It's a 2.4 meter inflatable antenna system that is very portable and can be packed into 2 cases weighing less than 99 pounds each. In this photograph on the left is the HiDAQ with the PULSAR inside the black box as well. There's also a small antenna that was used to transmit the data. On the right side is the receiving end, the GATR antenna, which feeds the signal to the PULSAR ground rack, which is then decommutated. For this test, the HiDAQ PULSAR was placed in the bed of a vehicle. The vehicle was moved about 100 meters downrange. The test was then conducted per the test plan. Here are the objectives. One of the more important objectives was to ensure that the bit error rate was less than 10 to the minus 6 at the receiving end. All 3 components had significant objectives. Here's the results. All objectives met. Quite a success. This is a plot of the power spectral density. The plot shows 24 signals total, 12 signals before transmission and 12 signals after transmission. They are overlaid on each other and appear as one trace to show the consistency. Here are 2 more plots of 24 signals. The top plot shows the amplitude over time. The bottom plot shows the phase correlation between all channels. All values are within the anticipated hardware specification. Tell me your name and your role.
All right, Dr. Larry Lowe, Vice President of Engineering here at GATR. The role in this program, so what GATR's developed is a 2.4 meter antenna that is extremely portable. So at the end of the day, what we're doing is we're letting air be the structure as opposed to carrying around a big heavy metal rigid frame to hold the reflector and the antenna components together. So this antenna you're seeing here, 2.4 meter antenna, when we're done we can take the feet off, disconnect the blower, unzip 2 zippers, the whole structure collapses to the ground and fits into a canvas bag. It's about 18 inches cubed and weighs about 20 pounds. So you get a real large aperture antenna and a real small volume. We had some funding from the space community. They wanted to see if we could make a deployable ground station, and so they knew that our antenna was already fielded with US SOCOM, the Marine Corps, the Army. It's already fielded in just general SATCOM use, and so they wanted us to make a ground station that could do full horizon-to-horizon coverage to track CubeSats. And so over the last 4 years we've developed this as part of the Kestrel program with the Space Missile Defense Command, and have demonstrated its applicability by tracking multiple satellites across multiple bands, S-band, X-band, Ka band, for instance. And so The application to what we're doing here with PULSAR and HiDAQ is that this is going to be something that's easily forward deployed. You can pre-position it in a multitude of orientations relative to a launch, and then it can track the rocket as it launches through the full launch cycle, pulling out the data that it needs. So you get the benefit of a real large aperture antenna, which is necessary when you're talking data rates getting up into the hundreds of megabits, which is the direction that we're going with this program.
Super. Okay. Can you tell me your name?
My name is Scott.
All right, Scott. I'm Arthur. Explain what your hardware does.
Our hardware is a ground antenna, and today we use it in transmit mode.
And it's easy to recognize because it's a big inflatable
Ball.
ball. There you
Yes.
go. Keywords. What size do we use on this? 2.4 meter? Is that
This is a 2.4 meter, yes.
What role did your equipment play in our test?
Our equipment was the antenna to receive data.
Okay. And what were your objectives?
Our objectives were to demonstrate that our large aperture, which has a very good signal to noise ratio, can transmit even on short distances.
Great. And did you hit your objectives?
Yes, sir, we did.
Awesome.
All right. This is the elevation axis, and it's on rollers. The other side of the chain's not hooked up, so that's when we just roll with that. Right now the motors aren't turned on,
Okay.
so once we hook it up, it'll be stationary.
You ready? I'm Bob Smith from Optical Sciences Corporation, and this is HiDAQ, our part of this demonstration for an end-to-end data acquisition telemetry system.
Yeah, so let me ask a few questions. So explain what your hardware does for us.
Our system is a complete high-speed ruggedized data acquisition system, currently configured with 12 channels, configurable to 48. It is acquiring data at high sample rates, moving data to a telemetry system. The telemetry system is connecting all that data down to the ground where it's recorded.
And that black box, that's your system, and that's it right there?
This HiDAQ or black box,
Okay,
yes.
very good. Okay, so what role does it play in this test today?
In this test, it's a complete standalone data acquisition system, high-speed computer. It requires data, it records it locally, takes the data, transmits it to PULSAR over a serial link, and that PULSAR takes that data and transmits it to the ground.
Great. Okay, so what were your objectives for today's test?
The objectives are to record data accurately on all 12 channels, move every bit of data to PULSAR, and have PULSAR get it to the ground and record it again on the ground.
Okay, and did you hit your objectives?
Everything went perfectly and has gone so for the last few tests.
Very good. Thank you, sir. Okay, tell me your name.
Dr. Herb Sims.
Okay, tell me about your hardware.
We have two sets of hardware. We've got a S-band telemetry system here, as well as a power supply that's actually embedded into the HiDAQ system. We also have over here our ground station near network rack that will take the transmitted RF data, down convert it, demodulate it, and store it to a hard drive for later retrieval.
So that's the transmitter, and that's the transmitting antenna right there?
Correct. We have a S-band patch antenna.
Okay. And so then that beach ball receives it, and then the beach ball sends the information to this rack.
Correct. We connect this rack up to the GATR antenna.
Okay.
And then demodulate.
Oh, very good. Okay, so what role does your hardware play in today's test?
We actually transmit. We take the data from the HiDAQ, we format it for nearest network compatibility standards, convert it to RF, comes out the antenna, goes to the GATR antenna, which then comes to this rack, gets demodulated, and then stored to a system that can actually output the data to the network.
Okay, very good. So what were your objectives for today?
Our objectives were to transmit the data error-free, maintaining our link margin that we have between our patch antenna that we've calculated and the GATR 2.3 meter dish antenna.
Very good. And did you hit your objectives?
Yes, we had error-free